speaker is Andy Neitzke from the University of Texas in Austin, and he'll speak about the WallCrossing Formula for 2D and 4D Donaldson-Thomas invariants.
Right. So thank you very much. I'd like to thank the organizers for the opportunity to speak here at this great conference. So I'm going to tell you about a WallCrossing formula for a new kind of Donaldson-Thomas invariant, which we call 2D, 4D Donaldson-Thomas invariants. And everything that I say that's original is part of joint work with Davide Gaiotto and Greg Moore. Almost everything I say is contained in a paper which appeared a few months ago on the archive. Let me mention for mathematicians who may be interested in this thing that paper is a very long paper, but there's a self-contained part of it, which is section 2, which contains the formula. So the formula I'm going to tell you, you can read just in one small part of this paper. A few things I say are part of work in progress, but OK, good. So what's this about? So in the last few years, there has been a sort of explosion of progress in this mathematical theory called the theory of generalized Donaldson-Thomas invariants. You're not going to have to know what those are. So the names that go along with this are Kontsevich-Soibelman and Joyce and Song, but also many others. Now, as a physicist, the reason why I got interested, Greg and Davide got interested in these things is that in many cases where these things can be defined, maybe in all cases, the generalized Donaldson-Thomas invariants, they have another name. They have a name which makes sense in physics, and they are the BPS state index, much like the indices Davide talked about a few minutes ago. They are a kind of BPS state index, which is counting states in a 4-dimensional quantum mechanical system with n equals 2 supersymmetry. And so over the last couple of years, there's also been a lot of progress, sort of parallel to this mathematical progress. There's been a lot of physical progress on these BPS state indices by many people. So this particular talk is motivated by some new progress in physics involving some new BPS state indices, which we call the 2D, 4D BPS state indices. And these things are not just defined in the context of a 4-dimensional quantum system. They're defined with in a 4-dimensional quantum system to which you add a new 2-dimensional surface operator, so a new kind of data. So we studied these things in physics, and we've learned a few basic facts about them. And in particular, one of the things we've learned is what their WallCrossing formula is. And so the main aim of this talk is to explain sort of these sort of rudimentary facts that we've learned about the 2D, 4D indices. And the reason for explaining these to an audience of mathematicians is that we conjecture that these 2D, 4D indices are really part of a new, not yet formulated extension of Donaldson-Thomas theory. So as Davide explained in his talk, OK, there's some extension, but still, why should you care about it? As Davide explained in his talk, among the reasons they care about it is that these 2D, 4D indices seem to be useful tools, even if ultimately your only interest is in the original generalized Donaldson-Thomas invariants. OK. Now, since I don't expect that you know, and in fact, I don't know what the definition of a generalized Donaldson-Thomas invariant in mathematics is, I have to focus on a specific class of situations where both of these, where the usual generalized Donaldson-Thomas invariants can be defined sort of relatively easily. A DT invariant is always supposed to be counting some geometric object. In this case, it'll be counting geometric objects that we can really get our hands on. There'll be some special trajectories. We'll have a Riemann surface. The only geometry will be that of a Riemann surface. We'll be counting some special trajectories on that Riemann surface. The trajectories are defined with the aid of some meromorphic quadratic differential. So that's the usual DT invariants. Now, in this context, I'll be able to tell you what these new 2D, 4D invariants are. And they'll also be counting some special trajectories, just trajectories of a slightly different sort. But that'll be our fundamental example. And I'll tell you what the WallCrossing formula is. Now, this 2D, 4D formula, though, is supposed to apply beyond this example. OK. So first, I'll review the old story, the generalized DT invariants and the ordinary generalized DT invariants and their WallCrossing formula as studied by Kontsevich-Soibelman. And then I'll give the 2D, 4D extension. OK, so what kind of mathematical objects are we studying? So let's fix a compact Riemann surface, call it C. with some marked points. It's important that it has at least one marked point on it. So I'll call these marked points Zi. There they are. Sorry, I have a slight notational glitch. So I goes from 1 to n. There will be an n later in this talk, which is not that n. It's not the number of marked points. Sorry about that. I don't believe the number of marked points will appear again in this talk, as long as it's greater than 0. So just for notation, if you delete them, let's call that C prime. And let's fix some parameters. At each of these marked points, I'll fix a complex number. And I want those numbers to be generic. I don't want them to be 0. OK, good. So on this Riemann surface, we're going to put some stuff. And the first thing we'll put is a meromorphic quadratic differential. Call it phi2. Meromorphic quadratic differential on the curve, which is holomorphic away from these marked points. And then at the marked points, it has to have a double pole. And the residues at the double poles are these parameters mi that I fixed before. So we're going to imagine letting this quadratic differential vary, but with holding its residues always fixed. So I'll let B be the space of all such meromorphic quadratic differentials. That's a kind of parameter space in our story. For those who know about DT invariants, it's like some slice through the space of stability conditions. So think of this phi2 as like a stability parameter. OK. So that's what we've got, a surface with quadratic differentials on it. OK, here's a little caveat. So in what follows, since this is a mathematical talk, if you want to know what's really proven, stick to curves of genus 0, because recently we learned about a possible glitch for higher genus. It may be just a technical thing. In any case, all the phenomena I'm going to discuss, absolutely everything I say, already occurs in genus 0, so you're not going to lose much. OK. So let's fix a meromorphic quadratic differential. In other words, a point of my parameter space. Well, once I have a quadratic differential, there's this well-known notion of the trajectories of a quadratic differential. Well, what are the trajectories? The fastest way I know of saying, well, a reasonably fast way of saying what they are is that if you have this meromorphic quadratic differential, then it defines a metric just by taking the absolute value of the quadratic differential. So what that means is right here. If phi2 is p of z dz squared, then the metric is just the absolute value of p. Well, to be exact, that's not really a metric on the whole curve, because phi2 can have zeros. So these little x's represent the zeros of phi2. And of course, we defined it so that it has poles. So this is really a metric only on the region where I've deleted those zeros and those poles. And it's a good thing that's not a metric on the whole thing, because it's flat. And of course, I couldn't have had a flat metric on the whole surface. So this is a flat metric on the complement of some collection of points. OK, so given a quadratic differential, I have a Riemann surface. Quadratic differential, so I have a metric on it. So now what am I going to do? Well, so now you can look at the geodesics in that metric. And if you look at sort of a typical geodesic, start at some point and go in some random direction, what happens is that you flow around the surface for a while, and eventually you wind up at one of the singular points, the singularities of phi2, so one of those blue dots. Now, that's what a generic trajectory does. Now, however, there may be, there typically are, a few special trajectories. So one possible special trajectory is one that runs. So if I have a trajectory, a generic trajectory, just both ends of it end on these poles of phi2. Now, if I have a trajectory that runs into one of the zeros of phi2, then I also have to stop because the metric is singular there. And so one special thing that you can have happen is you can have a finite length trajectory that just runs from one zero to the other. So let me call that a saddle connection. And if you have one of those things, well, if you have one of those things, it's rigid. It doesn't come in a family. And the second kind of special trajectory that you can have is you can have a closed geodesic, just like that, a closed geodesic. And if you have one of those, then that guy comes in a one-parameter family. So it sweeps out a little annulus on the curve. OK. So all right, I have a surface, I have a quadratic differential, then I can define these special trajectories. Well, I'm going to count these. Our Donaldson-Thomas invariants, in this case, are just going to be counting the number of these special trajectories. But I don't want to just count the total number of trajectories. I want to sort of classify them by their topology. And the convenient way of describing the topology of one of these things is to introduce just a little bit more technology. So if I have this quadratic differential phi 2, then it determines for me always a branch double cover of my surface. Namely, I just take the 2 square roots of my quadratic differential. So that's a canonical double covering. Because it was a quadratic differential, its square roots are cotangent vectors. So this double cover is naturally sitting inside the cotangent bundle to C. And then whenever I have a finite length geodesic, the finite length geodesic I can lift up to a closed curve on C just by taking both of its pre-images. So the point is, as pictured here, so if I have a finite length geodesic that ends on the 2 branch points, when I lift it lifts up to 2 curves. I'll take the union of those 2 curves. And those 2 curves are exactly meeting at the endpoints. The branch points are exactly the places where the 2 curves meet. So this thing actually lifts up to a closed curve. And now we can define our invariant. So our Donaldson-Thomas invariant in this situation attached to any homology class gamma. So let's let gamma be the homology class in the homology of the cover. The cover I call sigma. Uh-oh. What's wrong? Yeah. No. Good. The x's are the zeros of the differential. The blue dots were the poles of the differential. Yeah, because this occurs frequently, let me record it. I always have this problem. So now and forever, the dot means a pole of phi 2, and the cross means a 0 of phi 2. It is the notation I use. What do you mean? Yeah, these are the zeros of phi 2. The cross. Did I say it? It's a cross. Oh, you can't see it from there. Yeah, that's a cross. I'm very sorry. Orange. Can you see that it's orange? They're orange. They're also always orange. And the blue dot. That's why it's good to have redundancy in your notation. OK. Sorry, yeah. At this distance, it's extremely clear. Yeah.
So, are you really in the cotangent or the cotangent twisted by the poles?
No, this is really just in the cotangent. Oh, OK. I mean, the poles are deleted. I mean, the thing goes off to infinity.
So this is C prime.
Yeah, sorry. That's the cover of C prime. Yes. That's right. OK, good. So we're going to define our invariant. Our invariant is going to be really simple. So I look in each homology class. And if there's one of these guys, one of these saddle connections that lifts up to my class, then I say the corresponding invariant is 1. So that guy counts for 1. If I have a closed loop, I can also lift a closed loop up to just the union of its 2 lifts. That's also a closed thing on the cover. And that thing counts -2. And if I don't have either one of those things, then I count 0. And that's it. That's my invariant. It's an invariant attached to a surface and a quadratic differential. OK. OK, so now it depends on that quadratic differential. So suppose that I now vary the quadratic differential, holding everything else fixed, holding the curve fixed. What can happen is that the finite length geodesics, I vary this differential, so I'm changing the metric. The finite length geodesics can actually appear or disappear. And so in the parameter space B, this space of quadratic differentials, there are some real codimension 1 loci where this jumping occurs. So this is a picture of the parameter space with some walls drawn on it. Well, how does that actually happen? So I said it jumps, but why does it jump? So the sort of basic mechanism for what happens is the decay or formation of bound states. So what's a bound state? So here's a picture of some region of my curve C where I've got 3 zeros in the picture. And let's suppose that I've arranged my quadratic differential so that there are finite length geodesic from here to here, finite length geodesic from here to here, and then this third finite length geodesic that goes from here to here. So their corresponding homology charges are, if this one's gamma 1 and this one's gamma 2, this one is gamma 1 plus gamma 2. You just look at the lifts to see that. So what can happen? So as I vary my, so here the invariance would be omega gamma 1 is 1, omega gamma 2 is 1, omega gamma 1 plus gamma 2 is 1. So now, as I vary my quadratic differential, this picture will change. And what can happen is that this geodesic becomes closer and closer to the union of the other two. So it's passing closer and closer to that 0 at the top. And as I move my quadratic differential closer and closer to some wall in the parameter space, right when I reach this wall, this one actually degenerates into the union of those two. And then on the other side of the wall, I only have these two, and I don't have the third one anymore. So that's this phenomenon of wall crossing of Donaldson-Thomas invariance here in this very concrete situation. That's all it is. So here, omega of gamma 1 plus gamma 2 now equals 0. And so these invariants have changed. OK. Well, suppose I want to know how they're going to change. I'm not satisfied just with knowing that they could change. First question, where will the wall be? That question, it turns out, is easy to answer. And what you do is you define some functions on the parameter space of quadratic differentials, functions on B. Namely, for each cycle in this curve sigma, I just take the period of a canonical one form. Since we're in the cotangent bundle, there's this canonical Liouville one form. Just take the period of that one form over my cycle. So that defines for me, for every cycle here, so for every gamma, I have a corresponding number, which depends where I am on B. So then, so you can sort of readily convince yourself that the walls will occur exactly when two of these things are becoming aligned. So here, what's happening as we go closer and closer to the wall is that the z for gamma 1 and the z for gamma 2 are getting closer and closer to being lined up. What I mean by lined up is, so these are some generic complex numbers, and they're getting closer and closer to having the same phase. And the wall occurs exactly when these numbers have the same phase. So in general, that's where the walls will be. They'll be the places where these z gammas line up. OK. So that's where the walls are. But now you can ask the more interesting question of, well, how do I know what the invariants will be? If I know the invariants on one side of the wall, how do I know what they'll be on the other side? And that's governed by this WallCrossing formula, which Kontsevich and Soibelman wrote down. So as it should be for any example of generalized Donaldson-Thomas invariance. So I want to tell you carefully what this formula is. It'll take a couple of slides. And since I'm going to the work of telling it to you, I may as well tell it to you in a general setting, not just in this particular example. So I'm going to axiomatize my data just a little bit. So what was my data? Well, we have a complex manifold. In this example, it was the space of quadratic differentials. We have some lattice, which is keeping track of the charges of our states, the sort of topological invariant of our states, with an antisymmetric pairing. So in this example, it was just the homology of our cover with the intersection pairing. We have some numbers, z gamma. Those were just the periods of this canonical one form. And we have some invariants, which were just the counts of finite-length geodesics. So those are the sort of abstract data in which this Kontsevich-Soibelman formula is stated. So now, OK, you've got the data. Now I want to tell you the formula. To tell you the formula, I first do some little circumlocution. So I want to think of the z's in the following way. For every gamma with omega of gamma not equal to 0, in other words, for every one of these finite-length geodesics, I'll attach some ray in the complex plane. And this ray will be determined in a simple way. The slope of this ray will be just the argument of z gamma. So this ray just knows the phase of z gamma. And so as we move around in our parameter space, in other words, as we vary this quadratic differential, these rays are moving around. And in this way of saying it, the walls are exactly the loci where some set of rays actually become aligned. So here's, if I'm near some wall, I have a bunch of rays here corresponding to my non-zero dt invariants. And if I'm near the wall, some collection of them are very close to being lined up. So I've colored those in red here. And then as I vary parameters a little bit, those become exactly lined up, and now I'm sitting on the wall. So let's focus just on these sort of participating rays. So far, K was just an arbitrary letter. I called I just call it a K ray for no reason. So now I want to tell you the formula. So I have to introduce one more sort of auxiliary-looking construction. Namely, I have to introduce a torus, which is C star to some power. namely c star to the rank of gamma. And this torus, well, it's c star to the rank of gamma, so it has some natural coordinate functions once I choose a basis for gamma. Or to say it a little more invariantly, for every element of gamma, it has a coordinate function, just a map from t to c star, which are multiplicative. Or if I'm completely honest, there's a little twisting in the story. There's a little sign. Just ignore that sign. And now here's what I do. So for every gamma, I assign an automorphism of this torus, which I write just by showing you how it acts on the coordinates. It just multiplies them by this factor. And now what we do is, so remember we had a bunch of rays corresponding to a bunch of non-zero invariants. And now for each of those rays, we assign a corresponding automorphism, the automorphism k gamma. We raise it to the power omega of gamma. And now we take a product over all the rays. We take a product of these automorphisms. Well, that's a little tricky thing, because those automorphisms don't commute with each other. So to take the product, I have to tell you what order to take the product. And the order we take is just the order of the phase of z gamma. And then the WallCrossing formula of Kontsevich and Soibelman is the statement that this automorphism is actually the same on both sides of the wall. So this product is some big composite automorphism of a torus. And that automorphism should be the same on both sides of the wall. OK, what does that mean? Let's see an example. So let's suppose I have three rays that are very close to being aligned. And here I've drawn their central charges, Z12, Z13, Z23. So Kontsevich and Soibelman would tell you to form a product, to form this product of automorphisms. That's some automorphism of the torus. Sorry? Omega are my integers, my generalized DT invariants. So in this abstract formulation, they're just some integers. And I'm going to tell you how they jump as I cross a wall.
In the previous slide, the definition of the automorphism, when the pairing of gamma and gamma prime is negative.
Yes.
You mean that
birational.
Oh.
So yeah, I'm not worried.
Okay.
Yeah, don't be concerned. Think of x gamma as being a very small number.
That was what I was.
Think of this in some formal algebra. There's a way of making it precise, but I don't know.
Okay.
Yeah, that part is not a real issue. Yeah, so I have this product of Kontsevich and Soibelman tell you to make this product, and then so now as I go through the wall, these guys are exchanging their order. So now on the other side of the wall, they'll look like this. And Kontsevich and Soibelman would tell you to make a different product involving a priori different omegas. So the omegas may have changed as I go over the wall. And in fact, it's a simple algebraic game. Those automorphisms are given by some explicit formula, so you just work it out. And what you find is that these two things are equal just if omega prime equals omega of gamma 1, just if they agree on gamma 1 and gamma 2. But on gamma 1 plus gamma 2, the thing is shifted. There's a new contribution here. And this is this mechanism of formation of bound states. So it's a totally algebraic game. So this is what happens if the inner product of these guys is 1. OK, that doesn't seem very exciting. Why would you get so interested in that WallCrossing formula? So a more interesting example of this business is what happens when the inner product equals to 2. So then we can have this simple product, just k gamma 1, k gamma 2 on one side of a wall. And on the other side of the wall, that becomes rewritten as this enormous infinite product of stuff. So it corresponds to a wall where on one side, I just have two non-zero invariants, omega of gamma 1 and omega of gamma 2, corresponding to these two factors. And on the other side, I have some infinite pile of non-zero invariants. All of them are equal to 1, except for this one special one, which is actually equal to -2. OK, so for the physicists, this is the WallCrossing of pure SU2 Seiberg-Witten theory. But in our present geometric setting, we'll see it. Yeah, so what does it mean? So now the key fact is that I defined for you some invariants. And this WallCrossing formula that I just told you actually holds for these invariants. So for example, this simple formula, which occurs when the inner product equals to 1, just says that if I have two of those saddle connections that intersect at one point, and then I cross the wall where their phases align, then on the other side of the wall, a third saddle connection appears. And that's exactly the phenomenon that I showed you pictures of a minute ago. Now similarly, this formula, so here this crazy -2 appears, but we had an interpretation of the -2. So it says exactly that So on one side, I have two saddle connections which are intersecting at 2 points. And now on the other side, I have actually infinitely many saddle connections up here, plus this guy corresponds to a single closed geodesic. Okay. So far, so good. So I described a sort of simple class of enumerative invariants attached to a punctured curve. And I told you, I didn't tell you the proof, but I told you that they give examples of the Conceivage-Soibelman WallCrossing formula. OK, so now I want to make our extension, the so-called 2D4D version of the invariants. So actually, even the omega of gamma will be slightly refined. So the original data of omega gamma will be slightly refined to some new objects, little omega of gamma, gamma ij. I didn't tell you what gamma ij is yet, but I will. And we'll also introduce some sort of fundamentally new objects, mu of gamma ij. These mu's are the same mu's that appeared in Davide's talk. OK. So what's my data going to be now? This gray stuff is the same stuff I said before. The new datum is that in addition to these mark points where I had poles of my quadratic differential, I now introduce an additional point, which I'm just going to call z. And at this point, my quadratic differential doesn't do anything. It doesn't have any pole or any zero. It's just an extra point. Everything else stays the same. And so just as before, I'm interested in counting finite length geodesics on this curve in the flat metric determined by the quadratic differential. The only new thing is that now, in addition to the ones I had before, I allow some open ones. So I allow geodesics that have one end on this marked point z. And the other end will be on a 0 of the quadratic differential, as it was before. So OK, so now I want to count these new objects. And so just like before, I need to attach some sort of data that keeps track of their topology. Well, now they don't lift to closed curves anymore. What they lift to is some sort of open cycle, which has its ends on the two preimages of my marked point. And so what I get now is instead of a class in homology, I get some kind of chain with fixed boundary. So I'll let gamma ij, I and j should label these two points in the cover. The point is red. That point is red. That's a new point that didn't appear before. Red. Red dot equals new marked point. For a physicist, this new marked point is the surface operator. Yes. Sorry, I should have put a diamond or something. I don't know. So I'll let gamma ij now be the set of these open chains with these fixed boundary. So that gamma is not a group. It's not a group, but what it is, it's a torsor over the homology. So I can add closed cycles to these open ones. And now for any class in this torsor, I'll define a new invariant, which is even simpler than the other ones. It's just 1 if such a geodesic exists and 0 if not. OK. So that's part of my new sort of 2D4D data, is this very simple count. Now, in the presence of this extra point, we can also keep track of a little more information about the geodesics that we looked at before, because namely, we can look at their homology now, even relative to the. We can look at their homology on the covering with the preimages deleted. So we keep track of how the path moves relative to this extra point, and we encode that information in a new invariant, which I write omega of gamma gamma ij. So it's basically omega of gamma, but it keeps track also of how the path gamma relates to the other open paths. OK, never mind it. So as before, as we vary phi 2. So before I asked, how do these invariants jump when I vary the quadratic differential phi 2? Now I can ask an additional question, which is how do they jump when I vary my new marked point? So as I move my dot around the curve. And so now I have a bigger parameter space. Now just as before, these invariants can potentially jump. So this picture is almost like the kind of picture that I drew before. This is one of these open guys decaying into the union of an open one plus a closed one. So the open stuff interacts with the closed stuff. And OK, here's another thing that can happen, which isn't so exciting. OK, so now I want to tell you our 2D4D WallCrossing formula, our generalization of the Conceivage-Soibelman formula. it's because, so OK, indeed. So in the general context of this formula, I and j would be allowed to run from 1 to n. And so I would have, OK, so there's a general formula where I and j run from 1 to n. There's a realization of that general formula, which is almost like this thing, except with an n-sheeted cover. We'll come to that in a few slides, actually.
Are there also two reasons that begin and end on a red dot?
Well, that's just an ordinary closed geodesic. So,
red dot.
well, if they begin and end on the red dot.
Not the same one, two different red dots.
There's only one red dot. No. Downstairs, yeah. So it's a little.
Only one. You only allow one.
Downstairs, I put exactly one red. You could do more general things, but for the moment, I'm just talking about one red dot.
Okay.
Yeah. Yeah. So those closed geodesics that end on the red dot do play a role in this business, but I'm presenting it in a way that doesn't make that very manifest. But never mind. What I said is correct. No, I mean, I told you exactly the definitions. OK. So I want to tell you the So I want to tell you the 2D40 WallCrossing formula, and this is the most unpleasant slide of the business because I tried to write all of the data that's involved. Now the stuff that that's good because the stuff on the top you do not have to read because you remember it from before. So the stuff on the top is just the previous 4D data that I had. So it was, let me remind you, it was a complex manifold, a lattice of charges, so to speak. These central charges, z gamma attached to lattice elements, and some invariants omega that they're counting something. To that, we add now some more data, which is, so before we had this lattice gamma of charges, we now add some torsors, gamma ij. I and j can run potentially from 1 up to n. And moreover, of course, they're torsors, so they don't have a group law, but there is a sort of addition operation in the story. If I have something in gamma ij and something in gamma jk, I can add them to make something in gamma ik. So think of concatenation of paths with a common endpoint. And that has to satisfy some associativity condition. So in the example I've been discussing, n was just 2, and gamma ij was the space of 1 chains with boundary. Now then, the map z should be extended to be a map. Before I had z for z of gamma, now I'll also have z of gamma ij. And that has to obey an additivity. So since gamma ij is a torsor, there's a sort of obvious additivity you could have. So here the z gamma ij will just be the integrals now over these open paths of my canonical differential, canonical one form. And now there will be these two new kinds of invariants, little omega and mu. So little omega depends on a capital gamma and a gamma ij. But morally, it has essentially the same information as capital omega. It satisfies some shift property. So the dependence on this gamma ij really just introduces one new number. But these things contain the information of the capital omega. And then there are these new invariants, mu, which are counting the open geodesics. OK. So that's the abstract data of the 2D40 formula. So now, just as before, now this will be a rerun of the thing before. So we attach a ray. For every time I have a non-zero invariant, I'll attach some ray in the complex plane. So now we have two different kinds, which we call the k rays and the s rays. The k rays correspond to gammas that have a non-zero invariant, and the s rays correspond to these new open cycles, these gamma ij's, with a non-zero invariant. And the slope of the rays are given by the z's again. Now it's the slope of z gamma or z gamma ij. And as we vary in our parameters, these rays are moving around. And as before, the walls will occur when some rays become aligned. Let's focus on the rays that become aligned. OK, now, to formulate the WallCrossing formula I told you before, we used this little auxiliary gadget, which was a torus, right? C star to the rank of gamma. And the omega of gamma got encoded into some automorphisms of that torus. For the 2D40 WallCrossing formula, we have to extend that formula, but just a little bit. So we add a, on top of this torus, we put a trivializable. It doesn't come with a canonical trivialization. If those torsors were actually had a 0, then this would be trivial, but they don't, so it's just trivializable. A vector bundle over the torus. And the 2D40 invariants now will be automorphisms of that object. So what do I mean by that? So first of all, the little omegas contain just slightly more information than capital omega, as I told you. And so they determined, before I had an automorphism of the torus, now I'll lift that automorphism of the torus to also act on the fibers of the of this bundle. And so that'll be my new k gamma. We still call it by the same letter. It's somehow morally almost the same thing. But now we also have some new invariants, these mu of gamma ij's, and they give really new automorphisms which don't act on the points of the torus at all, but they're just some matrices that act in the fiber of the spectrum. So in fact, so those matrices also appeared maybe slightly implicitly in Davide's talk. So they're unipotent matrices just with one off-diagonal entry in the ij place, roughly speaking. Okay, so it's a holomorphic. I mean, they're just they're upper triangular matrices.
So they're an SL.
Yeah, in fact, let me just say GL. I'm not going to worry about that. So I want to show you that the formulas are as concrete as the formulas before. So this K and S, as I said, are automorphisms of some combined structure, which is a vector bundle over a torus. You can write down their action concretely on a basis of sections of the endomorphisms of the torus. So you have the x gamma that we had before. Those were functions on T. And now you also have some canonical sections, x gamma ij. Those are sort of elementary matrix sections of the endomorphisms of V. And I just tell you how it acts on the endomorphism bundle of V. It acts by these kind of formulas. So this formula is virtually the same formula we had before, just now with this little omega appearing. And this new formula, well, that's more or less the formula that was in Davide's. V was, I didn't tell you the exact definition of V. I just said it was a trivializable vector bundle. And trivializations, well, I can tell you. So trivializations of it correspond to a choice of elements in each torsor, right? Trivialization of the torsor. And then if I change the trivialization of the torsor, I change it by some gamma, and that corresponds to multiplying by x gamma the trivialization. Okay. That's presumably right. I can't think of it in real time. Okay, so now we do the same thing as we did before. We take a product over all of the participating rays of the corresponding automorphisms. And so what we get now is a slightly more complicated thing, an automorphism of this torus lifted to act on the vector bundle. And the 2D40 formula is the statement that this automorphism is the same on both sides of the wall. No, they don't commute. So the order, I mean, yeah, sorry. Yes, this is a product. Maybe I should have written two separate products. But the normal ordering is the ordering controls all factors of the product. Yes, the ordering absolutely matters. They do not. No, it's the other. It's the other way. The K is 4-dimensional. No, they do not stand for Kontsevich and Soibelman. The S stands for Soliton, and I can't really remember how we got the K. What's that? S could also be Stokes, yeah. Okay, so I have to go quickly. So far my story might seem a little bit lame because I told you a 2D40 wall-crossing formula that involves an integer n, but the only example of the 2D40 invariants that I told you had actually n equals 2. So there's a more general version, and this is the part that's a little bit in progress, although it seems to be mostly under control now, where the quadratic differential phi 2 gets replaced by a sort of k tuple a tuple of k differentials, so phi 2, phi 3, and so on up to phi n. And instead of just counting geodesics on the curve, we now count some more complicated gadgets, which are kind of, well, they could be just geodesics in some appropriate metric like before. So now we have various different kinds of, sorry, let me start over. These pictures for a moment, you can't understand what they are. What are they? Well, what we consider now is, instead of the two-fold covering, an n-fold covering. An n-fold covering of C, still sitting inside the cotangent bundle, just determined by these various differentials. Then we have branch points now of various kinds, where two sheets collide. And so I'm labeling the branch points by the numbers of the two sheets which collide. And now we have sort of different kinds of gadgets that can appear. We can have geodesics like before in a metric that's determined somehow by x1 and x2. Or we can have some more complicated things, some networks of trajectories where each of these things obeys a different differential equation. Well, one way of saying what equation it obeys is it's a straight line in the coordinate, which is the integral of xi minus xj. Xi and xj are two locally defined solutions of this equation. So you look at straight lines. Here's a 1-2 straight line. Here's a 1-3 line. Here's a 2-3 line. With fixed inclination, theta, and that theta has to be the same for all legs. Under that condition, you get, again, sort of a finite set of these kind of objects. But we don't know anywhere where these networks have been studied before. And we'd be very curious to learn of a reference, because from the point of view we're now taking, these are clearly sort of natural objects to think about. So it's a natural generalization of studying the trajectories of quadratic differentials, which of course are, that's been an object of study, serious study. Oh, so these actually are the analog of what I called closed before, right? Because the red dot. Oh, yeah. So there's okay. So there's potentially more complicated pictures where indeed you have one of these networks and then there's like a loop attached to it or something. We haven't studied those very systematically. They're allowed, and they presumably contribute to this business. Because I don't have too much time, and because we've mostly thought of, at least I've thought more about the A type than the others. But it's true. This is sort of there's an ADE story here, and this is the. It's presumably so. Yes. So we expect here there are, I would say, a few details still being checked, but we expect that the counting of these objects again, and their sort of open analogs where you have one leg ending on a marked point, is again governed by this the same formula that I just told you, the 2D40 WallCrossing formula. Okay. Now let me say this formula didn't come out of nowhere. So Chakotay and Vafa had previously studied, as Davide told you, purely two-dimensional field theories. And they gave a WallCrossing formula whose sort of formal structure was very similar to the structure I just showed you two examples of. You have a bunch of automorphisms, and you take the product of automorphisms to be constant. They didn't say it exactly that way at the time when they did it. That was back in the early 90s. But their thing can be rewritten in exactly this way. Now, in their WallCrossing formula, the group of automorphisms that appeared was really simple. It wasn't these infinite dimensional groups of automorphisms of a torus. It was just GLN, just a finite dimensional group. And our 2D40 formula, I mean, one way of thinking about it is, so this formula covered 2D field theories. Conceivich-Soibelman had to do with 4D field theories. And what we have is kind of a hybrid between those two. It's in some way sort of the minimal way of joining those two things together. And it fits into a sort of general formalism where the invariants are allowed to belong to some general graded Lie algebra. So from that point of view, what we're saying is that this particular group, the group of automorphisms of a vector bundle over a torus, is a particularly interesting group which sort of occurs in nature. OK. So what are these invariants good for? Yeah. Sorry. Yeah. So what are these invariants good for? Well, as Davide mentioned in his talk, if you are in a situation where these 2D40 invariants can be defined, then knowing the mu, the sort of 2D part of the data, the open part of the data, is enough to give information about the original generalized DT invariants. And in many cases, it actually determines omega. And so far, it's a sort of phenomenological fact. But these mu seem to be somewhat more easily computable. Skip the geometric. I'll say two words about the geometric application. So one of the interesting things that came out over the last few years was that you can use the Conceivich-Soibelman WallCrossing formula to give a construction of new hyperkähler metrics. You sort of start with a naive Strominger-Yau-Zaslow picture of some hyperkähler space. This is a torus bundle over the parameter space I had before. And then you correct it. You add corrections that come from these omega gammas. OK. In the example I was telling you here, this M is going to be a moduli space of solutions of Hitchin equations on the curve. What I want to say is that the 2D40 WallCrossing formula gives an extension of that business where this thing has grown some hair. So what does it mean? What it means is it has a vector bundle over it. I mean, it's just what you'd think, right? Now we've got a vector bundle over it. And this vector bundle has to get along with the hyperkähler geometry. It means it's a hyperholomorphic vector bundle. Think of hyperholomorphic as like a generalization of a Yang-Mills instanton. If M is four-dimensional, that would mean a Yang-Mills instanton. OK, fine. So in the case of the Hitchin moduli space, in the examples we've been discussing here, what this vector bundle is it's the universal bundle, the sort of universal solution of Hitchin equations. That's naturally a hyperholomorphic bundle over the moduli space. OK. Now, the last point is I feel like we should try to make some statement about what you expect sort of in general. So here I've laid out what we think is a 2D40 WallCrossing formula. There's some extension of Donaldson-Thomas theory. But I should say a little bit about how it should show up in situations other than the specific situation I've been describing. So what I say now will be sort of much more tentative than everything we said before. So roughly speaking, the picture should be that whenever you have a brane whose moduli space is 0-dimensional, we should, of type A or type B, say, we should be able to use it to sort of define a 2D40 version of the Donaldson-Thomas invariants that count the branes of the other kind, B or A branes, respectively. So it's a kind of funny-looking, maybe it's funny-looking, it's a kind of mixing of those two dual categories. So for example, suppose you have a Calabi-Yau threefold. So the sort of standard dogma about this situation is that there should be some generalized Donaldson-Thomas invariants which are counting special Lagrangian cycles. So I would call them A branes on X, where gamma here is measuring the topology of those things, meaning their homology class. So now suppose I fix a little bit of extra data, and this is probably not the most general extra data, but suppose I fix a class in the second homology that supports some finite collection of holomorphic curves, say n of them. So those are some B branes. So in that situation, with any luck, there should be a 2D40 version of these invariants, omega of gamma gamma ij and mu of gamma ij, where I and j go from 1 to n, and the gamma ij's are lying in some torsors for the third homology. That's the general story. But here I can tell you what gamma ij should be. There are 3 chains whose boundary is yi minus yj. So before we were counting closed special Lagrangians, and now we're doing something that's characterized by a 3-chain interpolating between 2 holomorphic curves. I'm not going to risk trying to say today how they should be defined. And that's it. So that's the conclusion.
Any questions, Brian?
Well, the usual BT invariant counting sheaf. So in this example, is there a sheaf version?
Oh, sorry. I was in the mirror of the usual situation. So that's right. So I guess the usual way of thinking about BT invariants is that they're counting some sheaves with characteristic classes 0, 2, 4, 6. So here I'm looking at this, what the mirror of that is supposed to be. So the mirror of that, in the ordinary situation, would be to count special Lagrangians, which is closed special Lagrangians. And now I'm asking, what's the 2D40 version of that? Now you might ask me, what's the 2D40 story in the original picture? So then it has to be sheaves which are in some way interacting, have some singularities along a special Lagrangian.
Other questions?
And the reason you're saying that the introduction of this new variable u counts the generalized Donaldson-Thomas invariant is because you're kind of saying the strictly saying statement sheaves on the mirror side get mapped to this chain of thing. Why do you think that this extra variable captures the generalized Donaldson-Thomas invariant?
Everything I said, everything I said in this talk, when I talk about the ordinary Donaldson-Thomas invariants, I always meant the ordinary generalized Donaldson-Thomas invariants. So they were always the ones that are studied by Kontsevich and so on, with the stability parameter and so on. This was supposed to be a further thing to add.
He's asking, can you explain why the mu determines the omega from the point of view?
Oh, I'm sorry. Let's see. I mean, I haven't internalized it enough to have a short slogan for it yet. It involves the stuff that was going on in Davide's talk, but I can't give you like a 2-word answer to that.
Any other questions? Yeah.
Sorry, for the other question, sure you should choose this by integer, but
Part of the purpose of this talk is to stimulate exactly such a comment. You're saying they should be sheaves twisted by an appropriate juror.
Right, and just, yeah, because you're going to put something wrong with the classification, please, you're represented by classification most problems.
Could be. I'd love to discuss it.
Okay, let's thank Andy again. The next talk is at 11 o'clock.